what I want to look at here is beats. You probably learned a little bit about this already. This is where we're looking at two different frequencies and the superposition of them, or the combining of them, and we get this beating effect. But I want to do it a little bit mathematically. So there's another little video where I talk about just combining two waves with the same frequency. You might want to check that one out. With beats you need different frequencies, so we'll call one of the waves y1, and this will be its equation. We use a cos this time, doesn't matter if you use cos or sine. This one has frequency f1. This is just 2 pi f or omega t. So at this stage we haven't included the wavelength, the kx, which you know from the other video. A y2, we'll make it the same amplitude, a0 cos 2 pi f2 t. So we've got two different frequencies. We're going to be looking at them at the same place. That's why we haven't really looked at the whole x thing. Remember, there are two independent variables normally with a wave, and they give you the position and the time. But since beats as a phenomenon happens in one place, we can forget about the x and just look at the frequencies. Now, if we're combining these two different frequencies, we've got basically two causes, cos A plus cos B. If we add those, we get 2 times the cos of A plus B over 2 times the cos of A minus B over 2. You probably know that from trigonometric identities. And if we do the maths on that one, we're going to end up with a wave that looks like this, 2A naughts. So as usual, we're going to get that whole twice as big amplitude thing. And if we put this all together, we'll get f1 minus f2 all over 2 times t cos 2 pi f1 plus f2 over 2 times t. So that's our combined wave, and it's got two parts here. And the two parts we need to look at are this back end bit and this front end bit. Now the back end bit, what's it basically saying? It's saying that the two frequencies are just divided by 2. They're summed and divided by 2. So that tells you that the basic wave now has an average frequency of the two. Okay, so the wave has an average frequency. It's this front end that gives us the interesting little bit right here. That bit there tells us that the frequency is actually 2 pi f1 minus f2 over 2. So it's basically saying that this whole bit at the back, is going to be modulated by this front bit. Now, modulated, that means that at certain times, because this is a time thing, not a position thing. Remember, with the standing waves it was a position thing, but with the beats it's a time thing. This cos is obviously going to go to 0, and when it goes to 0, basically turns off this average wave that we just looked at. So this is a modulating thing up the front, and it's got a frequency of f1 minus f2 over 2, which is half the difference between them. But remembering that for a wave you've got the plus and minus section, so although the frequency of this is f1 minus f2 over 2, it's going to happen twice a cycle. So the beats are actually going to happen at the frequency of f1 minus f2. A little bit tricky, that bit. Think about it if you didn't quite understand what I was saying. Now, if we draw this wave, let's see what it's going to look like. Should be all the same, those guys. What we're going to look at here is a wave that's going to look like this. So what's going on here? This wave inside the envelope has the frequency f1 plus f2 over 2. It's the average frequency, right? Now, the modulating section, if you like, the beats, in other words, are the things that are turning it off and on. So you can see on, off, on, off, on, off, on, off, and that's the beating that you can hear. And the frequency of that beating is F1 minus F2. It's actually got a frequency of F1 minus F2 over 2, but like I said, it happens twice a cycle, so the actual beating is F1 minus F2. So that's what you're going to hear at a single point when these two waves of different frequencies interfere.